All right, get ready to dive deep because we're tackling deep learning for AI. And not just any deep learning, we're going straight to the source, a Turing lecture with the giants, the legends, Yoshua Bengio, Yann LeCun, and Geoffrey Hinton.
Yeah, talk about a powerhouse of AI knowledge.
Absolutely. I always try to do my homework, so you sent over their paper, Deep Learning for AI.
Uh-huh.
And let me tell you, it's dense, it's thought-provoking, so I definitely need your help unpacking this one.
I am so ready for this.
The first thing that struck me, and maybe it's the most obvious, is how deep learning is like holding a mirror up to ourselves, to the human brain. It's not just about algorithms and data, it's about trying to understand and replicate how we learn.
It's such a fundamental shift, right?
Absolutely.
Like instead of lines of code, we're talking about networks of these artificial neurons all interconnected.
Like a brain.
Exactly. And
Yeah.
the more layers you add, the more complex it gets, the more it can learn.
Okay, paint that picture for me. How does it actually work? Like, how do we go from data to, well, deep learning?
Yeah. So imagine each piece of information, whether it's a word, a sound, even an image, it becomes a point in this huge multidimensional space. And it's the relationships between those points, the distances, the directions that actually hold the meaning.
So it's not just about the data itself,
Yeah.
but how it all connects.
Precisely. The paper calls these connections vectors of neural activity.
Vectors, like back to high school math class.
Exactly. Think about it this way. Imagine you plot the words Tuesday and Thursday on a map, but not by their place on the calendar. You're plotting them based on like how they feel, their characteristics, their vibes.
Okay, I'm with you.
They're both weekdays. They're both kind of in the middle of the week. They even feel similar in our routines, right?
Yeah, I can see that.
Well, deep learning can capture those subtle connections, those similarities in meaning, in a way that traditional AI just couldn't.
It's like it understands the vibe of Tuesday versus a Sunday. That's incredible. So we've got these networks, they're learning, picking up on vibes. But what was the real turning point? What took deep learning from interesting concept to like total game changer?
Well, the paper, it highlights a few key breakthroughs, but the one that always gets me is unsupervised pre-training.
Okay, break that down for me. Unsupervised free training.
So imagine like teaching a kid to ride a bike, but instead of, holding the handlebars, you let them watch other kids riding around first.
Ah, he's saying.
They're picking up the basics just by observing,
Right.
right? The balance, how to steer.
Right, they're getting a feel for it.
Exactly. And it's the same idea here. Instead of needing tons of labeled data, it's like we're saying, learn from the world around you, just like humans do.
So it's not about hand-holding the AI every step of the way. It's about giving it the freedom to explore and make sense of things on its own.
Exactly. Think about how much learning a baby does just by observing before anyone even starts labeling things for them. Unsupervised pre-training, it's trying to tap into that.
It's like giving the AI a foundation, a starting point, so that when it does encounter a specific task, it's not starting from scratch.
Exactly. And speaking of things that might sound complicated at first, the paper also mentions something called rectified linear units, ReLUs.
Okay, full disclosure, when I saw real use, I thought, oh boy, here comes the math.
Hmm.
But I'm trusting you to walk me through this.
Oh, it's actually simpler than it sounds. Remember we were talking about those layers in the network?
Yeah, like the more layers, the more complex the learning.
Right. So ReLUs, they're just a tiny tweak to how information flows through those layers.
Okay, so like what kind of tweak are we talking?
Think of it like a light switch. A normal switch, it's either on or off, right? But a dimmer switch gives you much finer control over the brightness.
Okay, so real use are like dimmer switches for the neural network.
Exactly. It's about fine-tuning that flow of information.
And this little tweak, it made a big difference.
Huge. It's actually a great example of how sometimes these small changes can unlock massive potential. ReLUs, they help deep learning models learn faster, become more efficient, and that paved the way for, well, pretty much everything we're seeing today.
Like the revolution in speech recognition. It's crazy to think how quickly we went from barely being able to type a text message to just talking to our devices like it's no big deal.
Absolutely. And it's not just speech. The paper talks about this competition, ImageNet, back in 2012.
ImageNet, refresh my memory.
Think of it like the Olympics for computer vision. Teams from all over the world, they bring their best algorithms and they compete on these image recognition tasks.
Okay, I'm picturing like a robot staring contest
Yeah.
with like thousands of pictures.
Yeah, something like that. So in 2012, this deep learning model, powered by all these advancements we've been talking about, It just blew the competition out of the water.
So not only can it understand what I'm saying, it can tell the difference between a picture of my dog and, say, a fluffy cloud.
Pretty much. It was a turning point, a real signal that deep learning was something truly special.
That's impressive. It's kind of mind-blowing when you think about how far this has already come, you know?
Oh, absolutely.
It feels like we're on the verge of, like, this whole new era of AI.
Yeah.
But then you read something like this paper, and it's like, hold on. There are still these big fundamental questions that even the giants are wrestling with.
Yeah, like how do we get deep learning to be more like, well, us?
Exactly. Like one of the things the paper talks about is how humans, we're incredible at learning from just a handful of examples. Show a toddler a picture of a giraffe once, and they'll probably recognize any giraffe they see from then on. But deep learning,
Yeah, it still needs so much data, right?
mountains of data. So is that the next big hurdle? Can we bridge that gap, make deep learning more efficient, more like how we learn?
It's a huge challenge, but the authors, they seem to think it's possible. They talk about something called out of distribution generalization.
Out of distribution.
Well,
Okay, walk me through that.
basically, it means being able to handle new situations, things you've never encountered before. Like you learn to ride a bike in your neighborhood, right? But then you go to a friend's house and the streets are different, but you can still ride, no problem.
Right, you adapt, you adjust.
Exactly. We do it without even thinking about it, but for deep learning, that kind of flexibility, it's a big deal.
So it's like it needs to be able to think on its feet, adapt to new environments without having to relearn everything from scratch.
Precisely. And beyond adapting to new data, there's also this question of moving beyond just perception to like higher level reasoning.
Like what?
Well, right now, deep learning, it's amazing at recognizing patterns, like identifying objects in an image or understanding speech.
Right, we've talked about that.
But what about things like planning, making complex decisions, understanding why things happen, not just what happened?
That's a whole other level.
It is. The paper actually touches on this idea of system one versus system two thinking.
Okay, I remember seeing that. Refresh my memory.
So system one, that's our fast, intuitive thinking, right? Like recognizing a face or knowing that 2 plus 2 equals 4.
Scott.
Deep learning, it's already really good at that kind of thinking. But system two, that's our slow, deliberate, analytical mode.
Let me think about this mode.
Exactly. It's how we plan a vacation or solve a complex math problem.
And that's where deep learning still has a ways to go.
That's the next frontier.
It's like deep learning has mastered the art of quick thinking, but the real game changer is unlocking that deeper level of reasoning, the why behind the what.
Exactly. And the authors seem to think the key might be cracking the code of unsupervised learning.
Ah, so we're back to that.
It all comes back to observation, to learning from the world around us.
Because as the paper points out, there's so much information embedded in the raw data we perceive through our senses.
Yeah, just imagine if deep learning could tap into that.
It could be incredible, like AI that doesn't just learn from labels we give it, but learns by observing, by understanding cause and effect, just like humans do.
That's the dream, unlocking the potential to model causality itself.
We've gone from mimicking the brain to potentially unlocking the secrets of causality. That's
Yeah.
quite a leap.
It really is, and to think it all goes back to this idea of getting these artificial systems to learn more like we do.
It's pretty amazing to think about how far deep learning has come, and even more exciting, even a little bit daunting, to imagine where it could go from here.
I know, right?
Well, huge thanks to Yoshua Bengio, Yann LeCun, and Geoffrey Hinton for their incredible work. And to everyone listening, I hope you're walking away with a little more curiosity, a little more wonder about the world of deep learning, because this is a field that's just getting started, and who knows what incredible breakthroughs are waiting just around the corner.